Hello, everybody. This is Unit 2.2. We're going to talk a little bit about that big glowing orb in the sky, the sun. So, just so you know, our sun is actually very average. It is not overly large, it's not overly small. It is a pretty plain G-type main sequence star. It's very basic. Some of the characteristics: its radius is almost 700,000 kilometers across. It's about 109 times the width of the Earth. Sorry, I should say the radius. So that's only half. The surface area is about 12,000 times that of the Earth. The volume is about 1.3 million times that of the Earth, and its mass is only 330,000 times that of the Earth, which means that its average density is actually quite low. It's only about a quarter of that of the Earth. So it's not the most dense object, but it's very large. Composition, it's mostly hydrogen, followed by helium, and then some small amounts of oxygen, carbon, iron, neon, nitrogen, silicon, magnesium, and sulfur. It's mostly iron or hydrogen and helium because hydrogen is the fuel that burns, that fuses, I should say, into helium, and that's what it needs the most of. When it starts running out of that, well, then bad things happen. Nuclear fusion is what powers a star, that produces the heat and the light, and you can see the different cores of the different layers of the sun and what kind of fusion is happening, with the most prominent being hydrogen fusing into helium. Um, you can see the different types of hydrogen. There are two different isotopes of hydrogen. Hydrogen isotopes fusing into helium while releasing two neutrons is what gives off the energy. So energy is released in that particular reaction. Some different parts of the sun. There are several different actual parts that we're going to cover. One is the core. It extends to about 25% of the radius. So it's the innermost part that extends out about a quarter of the way. Its density is about 150 times that of water. It's 15.7 million degrees, so very, very, very hot. And that's where almost all of the thermal energy comes from, because that's where hydrogen is fusing into helium. Fusion is contained in a self-correcting equilibrium, a state of very little change. So it basically keeps the same rate all the time. The next part is the radiative zone. It's the thickest layer. The temperature drops significantly down to about 7, all the way down to 2 million degrees in the outermost part. And its density drops from being extremely dense to only 1/5 that of water. So the density changes a lot from the core to the radiative zone. The tachocline is actually a really thin layer. It's more of a transition, and it's between the radiative and convective zones, created by very different rotations of the neighboring zones. These differing movements are potentially what generates the massive, massive magnetic field of the sun, because they are both working against each other. The next one is the convective zone. It extends from about 0.7 solar radii to near the surface, so it's about the outer 30% of the radius. The plasma here experiences convective currents moving heat outward, so the heat moves out, and then as it cools, it falls back in. The temperature drops to only 5,900 degrees Celsius, so still extremely, extremely hot, but nothing compared to the millions of degrees we were seeing in the core or in the radiative zone. The density is 1/10,000th the density of air at sea level, so it is super, super low density, very low density. The granular surface, so what we see on the outside of the sun, the appearance looks kind of granular. It's caused by thermal columns. So that's where the hot stuff is coming up, and then as it cools, it sinks back down. It creates this kind of a granular appearance in the outside. We have the photosphere. That's the visible layer, so that's also on the outside, and that's what we really see the most of. This is where photons are leaving, and that's what produces sunlight. They hit our atmosphere, and that's where we get the light from. And again, about 5,900 degrees Celsius. The density is now about a third of the density of air at sea level, so it's a little bit more dense than the other layer, the previous layer. And this is where helium was first detected, the first time we ever realized that helium existed. The atmosphere. So the atmosphere has different parts. It has the chromosphere, a transition region, the corona, and the heliosphere. Temperatures here get very high, so 1 to 2 million degrees in the corona, and the solar wind can peak at 20 million degrees. But what you have to realize is that's not as much heat as what you run into in the core, even though the temperature is higher. Temperature is basically the speed of the atoms, but the amount of atoms matters when you're talking about heat. So here we don't have as many atoms, but they're moving very, very, very energetically and very fast. The corona is visible during a total solar eclipse, and you can see that on the bottom picture. That's the corona. The outer layer, the heliosphere, is a layer of the sun that actually extends beyond the orbit of Neptune. So we are within the heliosphere. Solar activity on the left-hand side is something called the solar prominence. It's a large plasma ejection forming in the photosphere along magnetic lines. So it follows the magnetic lines, makes kind of a loop. In the middle, we have sunspots. Those are dark spots. And those are areas of reduced temperature because of some sort of reduced convection. So they appear really dark, and it follows kind of an 11-year cycle of high to low sunspot activity. Then on the right, we have solar flares. They are localized. They are the eruption of electromagnetic radiation in the sun's atmosphere. So it looks kind of like a solar prominence, but they go up and they come right back down. They don't travel in a loop that follows the magnetic field lines. So a few facts about the sun. It takes about 8 minutes and 20 seconds or so for the light to reach us from the sun. So if the sun ever stopped burning, we wouldn't know it for a little over 8 minutes. It's about 29,000 light years from the center of the galaxy, from the galactic center. It's galactic orbital velocity, so how fast the sun is moving around the center of the galaxy, is 251 kilometers per second. So we are moving very fast because we're moving along with it. One day for the sun is about 25 Earth days. Sorry about that. That's the bell here at Cooper. I'll wait till it's done. So, one day for the sun is about 25 Earth days. The sun is about 4.6 billion years old. It is a yellow dwarf, although it is mostly white, and it has about 5 billion years of life left. Eventually, it will turn into a red giant, eject its outer layers, and wind up a white dwarf, but we'll talk about that all later. And, of course, we know it as the center of our solar system. So there it is in the middle with all the planets orbiting around it. All right, I know I went really fast, but that's a lot of information, and you can always pause or look back over the slides or watch this thing over again if you really want to hear my voice again.